Hello, everybody. Before I go forward, I want to thank organizers for providing the opportunity to talk about RDMA on ARM. Also, I want to thank them for saving the best for the last. Apologies to the community. We have another 30 minutes to go before you enjoy nice Austin spring weather. My name is Pavel Shamis. I go by Pasha. I'm principal research engineer at ARM, focusing on enablement RDMA and off-chip interconnects on ARM ecosystem. ARM does not build interconnects. We're not an interconnect company. In a meaning, interconnects like you guys build big off-box, off-chip interconnects. Nevertheless, it's important for us to make sure that whatever you build, whatever software stack you create, run efficiently on ARM. And in this presentation, I want to share my journey about my experience of running RDMA on ARM. This is pretty much how it started. I got InfiniBand NIC, and all I had on my table, it was this nice little Cortex A53 based 4-core machine, clocked to 2 GHz. As you can see, it's too small to fit any PCI Express slot. Obviously, you cannot put any InfiniBand cards in it. Nevertheless, we used this machine for a while for continuous integration for ARM v8 based codes. We tested UCX, SHMEM on it, and so on. So it's very little, but very nice toy machines that actually may be useful. Joking aside, there is actually a variety of manufacturers like HP, Gigabyte, and so on that build servers based on ARM platforms developed by our partners like Kevium, Applied Micro, Marvell, Annapurna, and so on. So you actually may go today online and get one of the systems with PCI Express Gen 2, Gen 3 slot, stick InfiniBand card on it, and get stuff running. And actually, for my experiments that I will share later in this presentation, I used Soft Iron Box. But before we get into details, I would like to give an overview of ARM because many people not really familiar with the way ARM works. And I think it's important to understand in order to understand how we develop the software ecosystem. ARM is a world-leading semiconductor IP company and supplier, which means we don't actually build chips. If you come to ARM and say, can you sell me A57 chips? The answer is no, we don't build. We build and manage and run RoCE architecture, and we implement microarchitecture, various types of core, from very little to very big cores, implementing this ISA, but we don't actually build the chips. We have partners that license from us and build the chips. ARM architecture is used in majority smartphone devices, used a lot in digital cameras, consumer electronics, and so on. And there's two major types of licenses. There's ISA license, which essentially our partner just license the instruction set, and they may take the ISA, go aside, and build custom CPU based on this ISA. Or they may license from our microarchitecture, and we have a variety of different cores. One example is Cortex A72, 57, 53, and so on. It really depends on what problem you're trying to solve. In either case, whatever software you developed on ARM ISA, it will work on ARM architecture, and it will work on custom designs by our customers, since there's compliance testing to ensure that everything is compliant in our ecosystem. Besides building cores, we actually build a lot of building blocks surrounding the core itself. And on the slide, you have some of the examples, like cache coherent interconnect, Mali GPU, which is probably the most popular GPU in the world. We also built memory controllers and so on. Essentially, our partners may decide exactly what they want, what blocks they want to license from ARM, and essentially combined in whatever ways they want. Some partners just license the core, integrate with own cache coherent interconnects on own solution. Other partners essentially license everything and build solutions based on ARM architecture. In terms of business model, this diagram essentially describes how all it works. So ARM provides the IP. Our semiconductor partners for upfront license fee can license the ISA or microarchitecture. Essentially, they take it, they go, they build whatever they want to build based on ARM. Once they build and they actually start to ship ARM-based solutions, there is royalty associated with the chips. So by design, we have vested interest in to make sure that our partners are successful, because if they build chip but it does not work or nobody wants it, it's not beneficial for us, it's not beneficial for all the players in the ecosystem. Once it gets to the customers, we'll get feedback about solutions that our customer provide in working to improve the ISA, improve microarchitecture, and so on. Some interesting statistics. In 2015, ARM shipped 15 billion ARM cores. So it's around 400 cores every second. Some astonishing numbers. As I mentioned earlier, this is one of the exercises that our marketing team trying to do, fit all the partners into one slide. ARM role in this ecosystem ensures that all our partners are successful. So we have vested interest to make sure that software works, my architecture works, and everything compliant with ARM ISA. In terms of solutions developed by our partners, essentially, there is very broad spectrum what people build based on ARM. There is massively multi-core solutions like KVM Thunder X2 with 48 cores, Qualcomm-centric, Applied Micro. There is more customized solutions, sort of smart NICs, like Mellanox Bluefield, which is 100 gigabit VPI, InfiniBand Ethernet, with many A72 cores on it. And there is fully customized sort of accelerators, like the one from NXP, Xilinx, and Altera, which integrate ARM core with their FPGAs and their solution. And again, there's a broad variety of different microarchitectures of ARM with the goal that we design it in a way that you can find the right solution for whatever processor you build. In terms of recent announcements in HPC space, this two announcements coming from Europe this year. One is from University of Bristol that announced that we'll be building ARM-based high-performance system with expect to have more than 10,000 ARM V8 cores in it. Another announcement from Mont Blanc project that selected Bull Atos to build HPC system based on KVM Thunder X2 CPUs. This one announcement coming from Japan. So right now they have K machine in top 500. And in 2016 they announced post-K machines, this next generation supercomputer in Japan, which is developed by Fujitsu. And this machine is based on ARM architecture, ARM V8 architecture. Now I will share what is the status of our software ecosystem. So as our partners making progress on development of CPU solutions and so on, and we have some examples here that I already mentioned, AMD, Applied Micro, and so on. ARM and our partners have been working with open source community on enabling software stack and tools for ARM. We actively involved in OpenHPC, and I think last SC they released preview version of OpenHPC running on ARM. In a second, I will talk about compilers. There's also ARM performance libraries, and we offer commercial tools like ARM Code Advisors that help you to optimize code for ARM system, help to analyze your performance issues, and so on. There's also third-party optimized libraries, compilers, parallel debuggers, and so on. So there's a lot of work happens in software enablement space. In terms of distributions, all the main distributions support ARM today. It started a few years back, 2015. Distributions like Debian, Fedora, SUSE started to enable ARM support. Over the time, it went mainstream. Today, if you go to Red Hat, Ubuntu, SUSE, CentOS, to their websites, you can download ARM ISO for the distribution. And there's also ongoing work with FreeBSD community to enable FreeBSD on ARM. In terms of compilers, all mainstream compilers support ARM, GCC, C, C++, Fortran, LLVM. There's other commercial offerings from NAG and Pascal. There's also a compiler developed by ARM, which has special optimizations. For example, it has optimizations for scalable vector extensions, and it's also based on LLVM. And my general recommendation, if you get machine running with Linux on it, go and make sure you get latest, greatest compiler. Typically, this is the best way to get most of your machine. Another key player in enablement software on ARM is LINA organization. LINA is engineering organization. It has 32 members that fund the organization and contribute engineering resources to the effort. So there's more than 200 engineers, full-time engineers, working on LINA projects. And probably this only the organization that tracking the number, the amount of consumed coffee in their meetings. Besides coffee, they contribute a lot to Linux kernel and to a lot of open source projects. Generally speaking, this is a really good resource to go and get latest and greatest tools for ARM, latest compilers. They also have simulators and so on. Now we'll get a bit more in details about RDMA. So when I started the journey, I looked what we have running today on ARM. So Mellanox offered starting from 2.4 supports ARM. My suggestion, go and make sure you get the latest, greatest version. 4.0, I had really good experience, no problem. You install, brings all the kernel models and make sure that everything runs. Linux kernel, I had a bit hard time to pinpoint exactly when support for ARM RDMA was introduced. I think the general conclusion was when I talked with a couple of maintainers, starting from 4.5.0 and above, support for RDMA on ARM is functional. OFI distribution, I talked with Vlad a week ago. Seems like it's a bit behind. There is no ARM support in OFIT. And in the Linux distribution is essentially ongoing process. And it really depends on the way how distributions pick up the kernel from kernel.org. So as they continue to get newer and newer versions of Linux kernel, they start to gain more and more RDMA support in distributions. In Mellanox software, for example, what I saw when you install it, essentially, they bring all the models and everything in their tarball. So they have backward compatibility support for older kernels. For newer kernels, you may try whatever is available on kernel.org. For my work, I just installed Moffat because it was the easiest way to get the code running. Now I want to share some of the lessons learned, essentially experience on enabling ARM support. And essentially what I did, I went over UCX code, tried to compile, build, and run it on ARM. And all the gotchas that I stepped on, I share on the slides. So first important point to make is about memory model. Linux kernel community actually doing a great job. I have not seen any issues in kernel. It's all good. In user space, it's all different story. So in contrast to x86, which have relatively sequential ordered memory, on ARM it's relaxed memory model. So if you have assumptions about order of writes and reads, you have to make sure that you use barriers. And it's typically important in a couple of places, like multithreading. We have a couple of threads that you want to bound some buffer about, or shared memory, or interaction between software and hardware, which is essentially Doorbell and PCI Express. So typical scenario that we see is that there is some write of payload. I'm not sure if you can see it on slides. It doesn't show. There's write of payload on initiator side, and then it's following write notify. On the target side, typically you have some thread or process pulling on the memory on the notification. Is if you discover an update, then it goes and reads payload. In case of ARM, you have to ensure that you have write barriers and read barriers in right places. This is also true for some of the RDMA protocols. In this case, on writer, you actually have to do fence operation on your interconnect. But there's a couple of protocols, particularly in MPI, like RDMA, where you're doing RDMA write, following for by notification write. And on readers, it just pull for the memory. I stepped on a couple of codes where there was no barriers there. So make sure that you have the barriers. Low-level timers is easy. Again, I saw this mostly in user-level codes. It's all resolved in kernel. But in libraries like MPI, what people tend to do is, bypass classical APIs and directly go and read architectural timer. So, and in the code, you typically see if they have x86 and power. If ARM is missing, you just fail. And I just put example how you can achieve the same on ARM. So this is relatively easy to handle issue. This one is a bit tricky. I've been stepped on this in driver. On ARM, cache line size is architecture dependent. I stepped on a couple of places where people made assumptions the cache line 64 byte. This is not true for all implementations of ARM ISA. There are some implementations that use 128 bytes, others 64. In good case, you have asserts in the code that will yell on you that there is mismatch between user and kernel level cache line assumptions. In some places just silent, and then you may see drops in performance. So be careful about cache line sizes. Some other useful optimizations. So if you look at DPDK or UCX code, there's a couple of places where people use vector instructions for shuffling the bytes and initialization codes. So there's corresponding instructions in Neon, which is essentially ARM vector instructions. And I put a link to some examples how you can achieve the same on ARM. I tried it on A57. I did not see much improvement in performance. On the other hand, it didn't harm. So it's good to have, and it really depends on the way how particular microarchitecture implements this vector extensions. Another useful optimizations is wait for event. Essentially, on ARM, you have an instruction that you may wait on particular address to be updated. So typically, if you have spin logs, you will pull on some variable or some memory, checking if some change occurred. And by doing this, you spin the CPU full speed, and it's not very efficient. So alternative way of doing this is use WFE that essentially will pause the CPU, it will go asleep, and whenever its memory is updated, it wake up the core and the process running on it. And later in the slides, I will share some of results from my experiments. So some preliminary results, and the goal here really was to check if it actually runs. The goal is not performance. I used a lot of early enabled software. It's pre-production version of Moffett with head of UCX, XPMEM model was used for shared memory in OpenSHMEM OpenMPI master, running with Connectix X4 on soft iron AMD machine with A1100 CPU. On this particular platform, PCI Express is Gen 2 X4, so we cannot leverage and get full speed of 100 gigabit of EDR. It was capped actually by PCI Express bandwidth. So this overall view of the software stack that we use for this experiment. So we had HPC application or code on top of OpenSHMEM from OpenMPI, talking to UCX through UCX SPML level in OpenMPI. It talked to UCP UCX interface, which has 3 different passes. For shared memory, it can go XPMEM. It has implementation on top of verbs. And there are specialized optimized layer for MLX5 Mellanox devices. And again, there's some early results. What we see here essentially is that in terms of put bandwidth, pretty much you hit the capacity of PCI Express Gen 2 X8, and with both UCX on top of verbs and on top of MLX5, you achieve about the same bandwidth. There is slight difference in latency in atomic operations and put latency. There is quite substantial difference in injection rates. About 40% difference. MLX5 is faster than implementation on top of verbs. And this sort of expected the same similar difference we observe on x86. Earlier I mentioned usage of WFE instructions. So there's API in OpenSHMEM called SHMEM wait. Essentially it waits for memory update. And typical implementation, you just pull on the memory, occasionally call for some progress function. I changed the call to use WFE. So on the first plot in blue and red, you see different implementations. The blue one, it's using WFE. The red one, it's regular, just spinning. With both implementations, you see the same latency. In terms of number of executed instructions, it's more important number of executed cycles. We see substantial difference, which essentially shows that the core goes asleep and potentially save some energy. Unfortunately, on this platform, we didn't have any tools to measure the power. This is something we plan to do later on. And in other points, very little overhead is associated with this instruction. We don't see any difference in input latency. We also run some application-specific kernels. One example was HPCS SCA on top of OpenSHMEM, this Smith-Waterman DNA alignment algorithm. And so we observed similar behaviors with the message rates. This particular kernel does a lot of non-blocking puts and gets. It's sensitive to injection rates. In the red, higher is better. Sorry, it's lower is better. In the blue, MLX5 demonstrates a bit better latency than implementation on top of verbs. OpenSHMEM gaps. Another benchmark, essentially sort of trying to simulate graph-related problems. It goes over the memory and does random memory updates. We tried few different experiments with different allocations of the cores on the system, but essentially, again, this is injection rate sensitive benchmark. And we see that MLX5, with all the improvements that we had in the code, we observe better injection rates compared to the verbs. In this case, I think higher is better. And to sum it up, overall LinuxRDMA community have been doing a great job. I'm following RDMA mailing list, and people really careful about accepting the code and making sure that whatever accept into mainstream, it's actually portable code. A lot of progress have been made in ARM, HPC software ecosystem. And hopefully in OFA community, we'll see at some point offered release with ARM support. Any questions?